So in this presentation we will try to generate a cellular organization for this machine part incidence matrix using or explaining the procedure proposed by Boctor. So with this procedure, essentially we want to optimize the cellular arrangement. When I say cellular arrangement, what I mean is that given a machine part incidence matrix like this example, here you have 1 to 6 machines and 1 to 8 parts, and the number ones represents a visiting of a part on a machine. For example, machine 1 visit part 1 visit machine 1, 3, 4 and 6. Machine part 2 visit machines 2, 5 and 6 and so on. So given this machine part incidence matrix, let's try to demonstrate the use of Boctor's formulation, essentially using Excel. So I will divide this video in 2 parts. In the first part, just an introduction, and in the second part we will use Excel to implement Boctor's formulation. Just to mention that essentially real matrices are somehow bigger than this. This is just a small example to just clarify the procedure. So, given that Boctor formulation is an optimization problem, essentially we will have the 3 parts of an optimization problem. First, we need our decision variables, that is the first part. Then we need the maximization or minimization objective function, and finally we will have the constraints. So all the optimization problems have these 3 parts. So let's try to understand these parts in Boctor's formulation. So in Boctor formulation, the first part is the essentially decision variables. So here our decision variables are xik. Xik takes a value of 1 if machine I is assigned to group K. Yjk is 1 if part J is assigned to group K. So essentially I is the number of machines and J is the number of parts, while K is the number of groups. So in our case, in our specific example of this 6 times 8 matrix, I go from 1 to 6 while J go from 1 to 8. That's the first part of the optimization problem. Second part, the minimization function. In this case, the minimization function takes this form: Aij, absolute value of xik minus yjk. So here xik and yjk are binary variables. Maybe I did not mention that before. Essentially here xik takes a value of 1 if machine I is assigned to group K. But if it is not assigned to group K, then it takes a value of 0. The same explanation for yjk. Okay? So essentially xik and yjk are binary variables, either 1 or 0 for x, either 1 or 0 for y. So for instance, if a part and a machine belongs to the same group, then I cannot have an intercell move. Essentially, this function is trying to count the intercell moves. When can I have an intercell move? The moment that machine I and part J belong to different groups. Then I can have an intercell move. What is AIJ? AIJ is no other thing than the incidence value of this matrix. Okay? So for instance, A23, what is the value of A23? Is 0. A26 is 1. So AIJ is essentially the value of our machine part incidence matrix. So when can I have an intercell move? The moment that a part visit a machine, then I can have an intercell move. Maybe yes, maybe not. If machine and part belong to different groups, then I have an intercell move. Okay. If machine part and machine belong to the same group, both of them will have a value of 1, then this will be 0. Okay. So I will not have an intercell move if machine and parts belong to the same group. Okay. So this function is essentially counting the number of intercell moves. It's counting twice actually, that's why you need 1/2 here. Remember that k goes from 1 to p, j goes from 1 to n, where n is the number of parts, I goes from 1 to m, where m is the number of machines. That is the second part of our formulation. Finally, the restrictions. What are the restrictions in our case? Summation of yjk equal to 1, summation over k for every j. What this restriction essentially assures? This restriction essentially assures that each part is going to be assigned to just one group. The same for machine. Summation of xik, summation over k from 1 to p for every I should be equal to 1. This essentially assures that all the machines are going to be assigned to just one group. I can have some restrictions related with the size of the groups. We will see that later. Just pay attention that I can increase more restrictions related with the size of the cells. So let's say that I do not want a cell that only have one machine or one part. Then I can add some restrictions in that sense. Okay. So let's try to apply this formulation in this case for our matrix, for this specific problem of a matrix of 6 times A. So let's try to expand this. So if we apply this into this matrix, how many variables do we have? So the question is, if I apply the Boctor's formulation over my example of a 6 times 8 matrix, how many or what is the number of variables? How many variables? How many x variables will I have? How many y variables will I have? Well, that depends on the number of groups that you want. If you want two groups, then the number of x variables will be 6 times 2. If you want 3 groups, it will be 6 times 3, and so on. Something similar for the y variable. If you apply this formulation for a 6 times A matrix, how many y variables will I have? Well, if I have 2 groups, I will have A times 2. If I have 3 groups, A times 3. So in our case, how many x variables? Number of x variables? I will have, let's assume that we will try a solution for k equal to 2. I want 2 groups. Let's try this solution. 2 groups. So remember, xik, in this case I go from 1 to 6, so I will have 6 times 2. Essentially we have 12 variables here. If you want to see these variables, here I can expand for k equal 2. So I can expand this. If you want, this will be x 1 1. Another variable is for k equal 1, but I will have another for k equal 2, x 1 2, x 1 3, x 1 4, x 1 5, up to x 1 6. That's for the first group, 6. For the second group, x 1 2, x 2 2, x 3 2, x 4 2. So here I have to correct this because k take a value of 1, so all of these will be essentially 1 1. Sorry about that. This is also 1, this is also 1, this is also 1, and the one that varies is I goes from 1 to 6. 1 2 3 4 5 and 6. Okay, the same for the second group, x 5 2, x 5 6. Here I have the 12 variables. What about y? How many y variables do I have? What is the number of y variables? Remember, y goes from yjk, j goes from 1 to 8 and k goes from 1 to 2. So yjk, it will go, I will have essentially 8 times 2 variables. What are these variables in the long form? If k is equal to 1, I have to make the expansion over j. j 1 1, j 2 1, j 3 1, up to ja1, a variables. If k is equal to 2, y1 2, y2 2, y3 2, up to ya2. So I have a times 2 variables here. So hopefully it's clear the first part, the number of variables. Remember, these variables will take values of 1 or 0. Later I will use a computer to change these binary variables, either 1 or either 0, to try to minimize this objective function. So let's try to expand this objective function. If I apply this objective function over my specific example, how I will see this objective function in the long form. So let's try to see that. Maybe I can switch colors, because you are only seeing this formula: a I j times absolute value of x I k minus y j k. Let's keep in this initial notation. This is times. So let's forget for a moment the summation symbols. I can expand this. You see something that is very short because it's just an initial notation, but in reality this function is very big. Okay, so you will expand over k, because k will go from 1 to 2, and I will go from 1 to 6, while j will go from 1 to 8. Do you want to see this in the long form? This is the short form. So this is short, very short. Let's see in the long form. Let me switch colors. So in the long form, maybe I need to expand for k. Let's say for k equal to 1. For k equal to 1, this looks like aij times xi1 minus yj1 plus, you have another term for k equal to 2. Let me switch colors. You have another term for y equal to 2. So here we will use this yellow color. For k equal to 2, you have the term aij times xi2 minus yj2. Do you see? You can see how this very short expression, the moment that you expand over k, then you have two terms, and you can continue expanding, let's say for I. So let's work over this pink term, expanding it for I. If you expand this pink for I, so let's return to this pink color. For instance, for I equal to 1, what will I have? This term for I equal to 1 is going to be a1j times x11 minus yj1. You see? Plus, you will have another term for I equal to 2, you will have another term for I equal to 3, another, up to I equal to 6. Okay? So if you expand this time each one of these terms, let's expand this first term. This first term, let's expand over j. So I will use this blue color. If you expand over j, then you will have a11 absolute value of x11 minus y11 plus a12 absolute value of x11 minus y21 plus a13 absolute value of x11 minus y31 plus, if you want another term, a14 absolute value of x11 minus y41, and so on until j takes a value of 6. Here we are changing this index I from 1 to 6. You see how this term that I circle with this blue color essentially represents these 6 terms. So this green term represents 2 terms the moment that you expand over k. This pink term expand in 6 terms for I equal to 1. Six more terms for I equal to 2. So we can choose another color, maybe this. So here you have another term for I equal to 2. So for I equal to 2, essentially you will have these terms. A21, remember, here instead of I equal to 1, this time is going to be 2. So equal to 1 x to 1 minus y11 plus a to 2 times x to 1 minus y to 1 plus a to 3 times x to 1 minus y31 plus a to 4 x to 1 minus y41, and so on until 6, up to 6. Okay, we have finished expanding over j for I equal to 2. We need to expand over j for I equal to 3. So if you want to see in this way, here I will have another term for I equal to 3. 6 more terms for I equal to 3. So I will have another 6 for I equal to 3, another for I equal to 4, up to 6. Each one of these terms, how many terms does it have? This blue have 8 terms because we are expanding over j, and j goes from 1 to 8. Sorry if I did not explicitly explain that. This also I will have 8 terms. I thought before I said 6 terms. Essentially 8 terms. 8 terms. 6 of these groups, each one with 8 terms. Remember, this is just for this pink. Okay? We still need to expand for this yellow one. It would be something similar. Let me do this expansion here. The yellow part looks like this for k equal to 2, remember. For k equal to 2, the yellow part looks like this: aij absolute value xi2 minus yj2. So let's try to expand this. Essentially this is the same as you can see here: xij times xi2 minus yj2. Here is xij times xi2 minus yj2. How can we expand this? We can expand this if we switch colors for I equal to 1. For I equal to 1, I will have a11 times x12 minus y12. I'm expanding over j for I equal to 1 plus a12. If you have problems understanding this, maybe you will require a previous step. For I equal to 1, what is the form of this? Essentially will be a1j, okay, because I takes a value of 1, this is 1, x12 minus yj2. We are still not expanding over j. So in the next step I can expand over j. Then you see a11 times x12 minus y12 plus, this is absolute value, plus a12 times x12 minus y22 plus a13 times x12 minus y32. You see how this term x12 do not change. You see, in all the terms you have this term x12, 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 because that is how it looks. 1, 2. We are expanding over j. J will go from 1 to up to 8. So we have 8 terms for I equal to 1. Something similar for I equal to 2. Something similar for I equal to 2. So for I equal to 2, how this expression looks: a2j absolute value of x22 minus yj2. So if I want to expand over j, how many terms? 8 more. a21 times x22 minus y12 plus a22 times x22 minus y22 plus 823 absolute value of x22 minus y32, this up to a. You see how this term, for instance, does not change and appear in each one of the terms. This I need to repeat for I equal to 3, for 4, up to 6, because I go from 1 to 6. So I have 6 times 8 variables. You see how this pink term for k equal to 1 represents 6 times 8 variables, 6 times 8 terms. Here are the 6 times 8 terms. You see? While this yellow term represents 6 times 8 terms. Where are these terms? They are here. You just need to continue doing this. So essentially this initial notation is a way to compact this expression. You can compact even further. Here, just in one expression, you have 2 times 6 times 8 terms in just one small term. So we will try to implement this in Excel, maybe, or any other software to create this function. So remember, we will have a lot of terms here. 2 times 6 times 8, because we are only working with this small matrix. If you increase even more, you will have more terms. Okay? In Excel, maybe we can do something an improvement. Let me explain that improvement in Excel with the second term. You see this matrix. We can think this in a matrix form. You see this term A11, A12, A13. A11, A12, A13, here A21. Okay, so maybe I can think in this like in a matrix, where here I will have A11, A12, up to A18, downwards A21, up to A26. So I will have a 6 times A matrix. We can call this an A matrix, maybe Aij matrix, times, because we are multiplying times, another X matrix. This X matrix, you see, is formed with x12, x12, all this row is the same, x12, 8 terms. Next row is x22, 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 8 terms. And you can continue doing this 6 times. So this is again a 6 times A matrix, minus another matrix here. This matrix is y12, y22, y32 up to 8. Similarly downwards we have y12. Oh, it's the same vector. y32, how many times? 6 times. 6 times a. So I can do this. Just have a matrix minus another matrix. I need to take the absolute value. So here I need to essentially group this and take the absolute value, and this absolute value I need to multiply times a. That is something that we will do in Excel. Instead of working with this very long equation, we will try to express in this matrix form. This was for this yellow term. I can do something similar for the pink term. You have an A matrix, an X matrix, and a Y matrix. So we will have these three terms: an A matrix, an X matrix, and a Y matrix. So let's try to do that in our next video.